This individual has been in astronomy for more years than he wants to talk about. And his name is John Briggs. We all know John. I remember one time he was telling me about working in an observatory, and they were making a movie. And they were trying to direct John, and they didn't know what to call him. So I guess
it was Keanu Reeves. You got to give, yeah.
Oh, there you go.
Keanu Reeves. Okay. Keanu Reeves.
And said, have the telescope do that, you know?
No, it was more like, have the telescope do.
Yeah.
No, the actress was at Yerkes.
It was at Yerkes.
And it was chain reaction. It was disappointing in many respects.
So John, needless to say, is known as the telescope
dude.
In our and he's here to give a presentation on just some observing in Colorado. Colorado's a state. They think they have a hockey team. At least in my son's eyes, they do.
Yeah, no, here it comes.
So he's just about ready there. He's got a lit keyboard.
There.
There we go.
Kind of scrambled the brain, but anyway.
Okay, so I'm going to turn it over to John. Thank you. Here we go.
Thank you. Yeah, that anecdote was being recalled there was at Yerkes, and the movie was Chain Reaction, and for about a month, several of us at Yerkes were being paid by 20th Century Fox, and it was an action movie starring Keanu Reeves, and he was really quite the gentleman, actually. But an actress was supposed to be the astronomer at Yerkes, and he was escaping sinister forces in Chicago. And he was a Chicago scientific technician, basically like I was, and other of our friends. But he came up to Yerkes, and the actress was supposed to be the eye end of the 40-inch refractor, manipulating a plate holder and the guide paddle. And so she was sitting up there prettily enough. But Keanu was just sincerely concerned that she made the right motions with the guide paddle. So he called upon me to advise her the best I could. What was the other funny thing about that? Yeah, they would work till about 2 a.m. And for maybe 14-hour days. And they'd get night shots. And anyway, but one night after most everybody had left, the director himself and his most immediate creative team, because they were kind of writing this on the fly, we were really eager for them to look through one of the telescopes. And I said to him, hey, we got the 40-inch reflector on a globular star cluster. Can you walk up the tower and come see? And they were all exhausted, but they came, and we looked at M13 or something, and the director took a look, and it moved around under computer control, and he said to me, about how much would a telescope like this cost? And I thought for a second, and I said, well, maybe to replace it, maybe about $800,000, my best guess. And he said, that's about how much money we've spent on the writers for this film. And it was a beautiful irony, because he knew the money was much better spent on astronomical hardware. Okay, anyway, where's the PowerPoint? PowerPoint. See, they kind of scrambled this brain. Early photography from Colorado. First act, yeah, here we go. Let's see if it works. So I work for a non-profit foundation now in Colorado, and the slide, you can't think when you're there. It is here, and then begin from beginning, right on. Good. Okay, and so
you can do everything with the
yeah. Too many things you can't do nothing. Push the main. Well, I'll do that in a second. So I work for a non-profit foundation. Eagle, Colorado now, which is near Vail,
And we have a 16-inch EFM in a beautiful dome, and I'm doing a variety of different things there, including local school outreach. And we have a couple of nice CCD cameras, but really I have not done color photography before with CCD, so I'm learning as I go. And so Mario sets examples of inspiration and stuff like this, but now that's out there. Do I point it at this? What do I do?
Ask the telescope.
Yeah, the telescope, dude. This is graduate. Where the hell with this thing? I'm just going to do this. There. Yeah, here. I don't know why. This is too much. So anyway, it's at about 8,600 feet, and it's a 16-inch DFM in a nice little dome. And I'm trying to learn how to get good star trails with a digital camera. I only took this hardly a week ago, and I'm working on it, but I've seen better things on the web, but maybe they're involving Photoshop. That's a daytime shot of the summit. The dome's there behind the trees. It's very pretty. And that's the telescope. And to many of our eyes, things like this are more pretty than flowers or trees or anything like that. But it's got a TeleVue 5-inch piggyback on it. And we've got one of these new S-Big CCDs with the big chip. But the autoguider didn't seem to be working on it, so we're sending that back to get the autoguider fixed. But hey, there's always something. And there's a nice control room, and it all works pretty slick. But I wanted to quickly get some very basic astrophotos so that I have something to share with local schools. And that's all I happen to have on the laptop. I'm going to show you those. This picture, though, was taken by my daughter, Anna, when she's 12. And we just put a Nikon camera body on it, and it's easy to get pictures of the moon with a good telescope like this. But when I go to schools, I try to show pictures that I can honestly say, well, this, it's really the stuff that looks scary, technical, big telescope when I show the students the pictures. But I can say honestly, but I just showed my daughter how to put our own camera from home on the telescope, and my daughter took this picture. And it's really not such a big, complicated deal as you might assume. That's the way I try and approach it when I visit classrooms of young students. Now, the first camera that was immediately available when I got out there was, we have an apogee with science filters, photometric filters, not the blue, green, red luminance filters that are normal for color photography. And I hadn't done this stuff before, and all we had were these like photometric filters that were only very approximately blue, green, red bandpass, but I used them anyway, and I was trying to photograph the brightest, most spectacular thing in the sky that at least get some results. So here's the dumbbell Nebula M27 in kind of bad scene, but it's a half-inch square CCD on this camera with a 16-inch f8. The image scale is fairly big, and this has also been 3 by 3 pixels because they're seeing is bad compared to the small pixel size, but it was very gratifying to me to be clicking on CCD soft, or I think that's the program I was using, to get any color result at all. And it's also exciting for a beginner in color CCD photography, to so trivially record the fact that the central star in a planetary nebula is distinctly blue, like I've read about in books, because they're shining very brightly towards the ultraviolet. They're real hot stars. And, that kind of stuff comes streaming through when you do this, and that's kind of fun. Now, this was taken nearly a year ago, this picture. We have a new camera now that has the appropriate color filters that make the realistic color reproduction more easy just with the nominal camera settings. This is a bigger chip, so the same object looks smaller. The color balance is different. It looks more like the pictures I've seen in textbooks, but the central star still looks kind of blue, and it's just neat. And this is not a real fancy shot, in that it's just 4 2-minute exposures through the luminance filter, which is fundamentally a clear filter, and then the other 3 for the color effect. And it's fun learning how to do this. I gotta kind of show them that I know how to do something. So anyway, here's the little dumbbell with an S big color camera. Look at that big orange star in the left-hand side. So I'm just going to go through some of these. The Crab Nebula, and these are, I'm just trying to emphasize, these are a beginner's color photography with what this wonderful technology allows. As I get more sophisticated with the processing and understanding the art of managing your signal-to-noise ratio, it's all about understanding the signal-to-noise ratio and increasing your exposure time without allowing your effective exposure time, without allowing things to become saturated, so you're constantly increasing your signal while beating down the noise. And it's very interesting learning about how to do that. Good old M103, the one up in Cassiopeia that looks like a little triangular open star cluster. Couldn't resist doing it. This was actually with a scientific camera that didn't have the right color balance, but you could still see that there's a big orange star among the other stars in the open star cluster, and I think that's something I could notice in high school with a 6-inch refractor, that there wasn't color contrast among those. Kind of fun. This is the, at a glance, you think, oh wait, Orion Nebula? No, it's that other nebula in Orion above and to the east of the belt. What is that, M78, is it? 78, anyway, it's fun, it worked. Except, is this one that got the airplane trail? Yeah, there's a bug on this screen, but that's here, not there. Yeah, there's a green, and during the green exposure, it doesn't show up so well in the projector, but there it is. It's not really an airplane, it's a satellite, I guess. You get, or whatever it is, you bump into all kinds of rubbish, especially near declination -5 or -6. If you observe down there, there's all kinds of geosynchronous satellites that very annoyingly drift through the field of view. Just the other night I was trying to do M11. All kinds of rubbish came creeping through the exposures, and then I looked at the declination right around -5. That's where, from latitudes like ours on Earth, the geosynchronous satellites are hanging up there, so you track in the sky and move through the geosynchronous satellites, and they're quite annoying. The Flame Nebula, just to the east of the leftmost star in Orion's belt. So yes, and so it's a fun. Most people, of course, don't know about this, but almost everybody knows about Orion. So you can explain that the glare is from the star that you've all seen in Orion's belt. But if you know to look for it, there's this wonderful nebula right beyond it. You can only barely see it, maybe in a 5, maybe 6-inch telescope to begin to see it. But boy, does it come screaming through the Flame Nebula with even relatively short exposures with modern detectors. This is the globular star cluster down there under Olympus. Which one is M70 what? 9?
79.
Gee, amazing. I can remember the numbers on the spot here, but I can't always. But there's a lot of blue stars, it seems to me, in this one. That's what I thought when I saw the picture. It has a lot of blue stars. So I reached for Burnham's handbook and read about the darn thing, and sure enough, in Burnham's handbook, they talk about there's a lot of blue stars in this particular cluster. It's wonderful to see these things and be more inspired to read the details and gain a little bit deeper understanding. M33, and it was very gratifying to get a shot that detailed when, in fact, I didn't particularly know what I was doing. I did get auto guiding going, and that is important. And sometimes you have to build a custom cable with with something like a DFM. It doesn't automatically plug in. Auto guiding is very important. And Mario had shots like this showing the Hubble variable, but it's so amazing that we can so really trivially record, I guess they probably supergiant stars in the spiral arms of another galaxy, Andromeda Galaxy here, M31, but actually stars in another galaxy. That's just really, really... Edgar Everhard did it with hypersensitized 2415 film back in the early 80s. He was a real pioneer of optimizing the high-resolution 2415 black and white film for astrophotography. And I worked for him for a while, and he was so excited and thrilled back then to get shots like this in black and white, where you could, with a 16-inch telescope, you could do what only like a 100-inch telescope could do at the turn of the century. But this stuff has become relatively trivial to do with electronic detectors now, and it's cool. NGC 253. It's got a rhythm to it. And then the Edge-on one in Andromeda. What is it? 891. New General Catalog 891. I like the Edge-on galaxies because they're real cosmic looking. Wasn't it on Outer Limits or one of the old science, black and white science fiction shows? They showed some shots, and including like an edge. It might have been this very Edge-on galaxy. You see this when you're 8 years old on black and white TV, and I don't know, you fall in love with Edge-on galaxy. So the progression of these images, and there really aren't that many more. I was working from things close to Earth to farther away from Earth, and some galaxy clusters here, or at least a galaxy with companions around it. And I set up a subscription, as anybody can, to the electronic telegrams from International Astronomical Union. And so this is the way to hear, you know, what's happening in the sky. Anything very ephemeral, people talking about the supernova up there in the whirlpool. This is the way objects like that are announced. And so this is an example, way back last year, an announcement of a supernova. And of course, I jumped on it, and it was just fun as a dramatization to local students. You don't see the galaxy very much, but it's a little bitty hard spiral there. And I took this picture, and I didn't know for sure that I was seeing the supernova. But when I compared this picture to ones of the same object on the internet, well, sure enough, that guy right there off my fingertip, that wasn't on the internet pictures. So supernova going off in this other galaxy. And when you just think about it, what it represents in terms of the energy release there, so long ago, so far away. But what bad news that might represent to somebody all too close to it, because it's so much energy. The thing is, as well as provocative, of course, to think about all these things. Stefan's quintet, Mario showed a shot of this that I think was a heck of a lot better, but I'm learning. And I don't even remember. This was just a random field with a lot of little galaxies in it, a much more distant galaxy cluster. And this is going back to a black and white chip with a science filter. I mean, I just, okay, this thing is what I was working to. Is it working? Yeah. Let me just see. Oh yeah, it's working. Can you see anything funny about this? It's flickering a little bit. Because it is, in fact, it's a little time series. It's 7 exposures. This is more what I'm personally especially interested in. Hopefully that wasn't a laptop. It wasn't. It's 7 exposures. Each one was 3 minutes long. And there was essentially no time between the exposures. So they're just one after another. And so, well, let's see. Oh, look, where's the, I gotta get it. Oh yeah, looky there. Bloop, 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 bloop. Bloop, 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 bloop. What is it, aliens? I asked the youngsters. Because if you look around, where's another one? Oh yeah, look up here. Bloop, 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 bloop. Let's find more. Oh look at this one. Bloop, 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 bloop. They're fun, huh? Asteroids. So what you do, is you're running your telescope, you're pointing it with the sky software. You click on the sun, you get the coordinates of the sun. Well, the sun is set, but then you just add 180 degrees in the, well, you figure out exactly the opposite coordinates on the celestial sphere. Simple arithmetic. So if you point your telescope in that direction, exactly opposite the sun, so that's where the asteroids look brightest. And you get a lot of asteroids, well, there's asteroids all over the sky, but they're particularly bright in the so-called opposition point. And I wasn't pointed exactly at the opposition point, turns out, because I noticed on the computer-generated sky map that there was a distant galaxy cluster in the sky, just within a degree or two of the opposition point. So there's a central galaxy in this cluster, and when it's not being blown up so much, you can see that there's a lot of little galaxies, really all, there's one. There's a galaxy cluster there. It's quite provocative to think about how far away they all are, but we're looking there. And if you sit down on a good monitor, wearing your reading glasses, and with a beer or something, you can find there's 7 or 8 asteroids, counting the little faint ones, all in one shot. And of course, that's a lot of fun. I'd like to try and get a shot that where you can see, well, 30 of them or something. I don't know if I'll pull that off. But what you can do, if you're willing to spend $35 to get this piece of genius shareware written by an Austrian some time ago, it's really easy to make measurements of the celestial coordinates of things in a CCD frame. This software is called Astrometrica. And like I said, it's a shareware download, and there's a few technical steps. You got to learn what buttons to press and things of that nature. But it makes the measurement of moving objects quite trivial, at least compared to how it used to be. And if you can measure these newly discovered things, you can report that information to the Minor Planet Center of the International Astronomical Union, and they use those measurements and the associated times to compute, to upgrade the orbital calculations of where things are going in the sky. So that's just one example of a productive thing a small observatory can do. And this particular software automatically creates an email in just the right format that looks something like this as you make your measurements. It used to be that it took an entire man-day of effort to do everything required to make a single astrometric measurement of a moving comet or asteroid with equipment. Nowadays, you can produce the same measurement and have it generated into an electronic report like this, in principle, in only a few minutes effort for $35. The measuring engines, the instruments required to measure the photographs in the old days, very fancy microscopes with XY stages, they probably cost, no fooling, back in the old days, $35,000, because the ultra precision machining, you know, with accuracies down to like on the order of a micron. Anyway, if you've done it the old way, you can't help but be sort of enthusiastic when you see how powerful the modern techniques have become. You can get more done more quickly, and so then, when you get one of those International Astronomical Union electronic telegrams, say, talking about a new comet like this one, you go running out to your telescope, and you get your picture of the new comet. And if you get the exposure just right, maybe not quite as long as this one, it becomes very easy to measure the head of the comet relative to the reference frame established by the background stars. And that's one of the things we're doing out there. And it's a lot of fun. And that's the end of that very hastily edited PowerPoint. I could show a little bit more of something, but that was mainly what I wanted to show you right now, so thank you very much.
Actually, before you sit down, John is actually our last speaker. And does anybody, do you have that?
I do have.
Show of hands. I can't see, so there we go. Would you like to see some more?
I have
okay, there we go.
Just a little bit. Yeah, it'll only take another 5 minutes.
5 minutes is fine. We have, while John's going to set up for that, it was kind of interesting when we talk about planets and we talk about the changes we've seen. I asked someone today how to surmise that for youth, and I was told the easy way is to explain the fact that there are now 8 planets and a lot of icy crap. So that and really, if you think about it, that's a lot of what goes on. So it's back to John again. Thank you.
Okay.
John, that Clark right there.
That Clark is like a 6 1/4 inch Clark that was at Hebron Academy in Hebron, Maine for many years, and it's dated 1895. But back about 1980, as an obsessive, compulsive young man, I took the time, of course, not an obsessive, compulsive old man getting there, but I drove up there to Hebron Academy to see this instrument. Because in the first edition of the Smithsonian book that I happened to glob onto a copy of, it inspired me, it described this instrument, but I didn't know any better. There was a typo. It described the instrument not as 1895, but as 1859. And I was oddly interested in these things, and I could tell that, wow, if it's an Elvin Clark telescope from 1859, that's pretty wild and early. I'm going to go up and see it. So I borrowed my old man's car or whatever, went up there, and was somewhat disappointed to discover this in 1895. But for whatever reason, although it came into being the Antique Telescope Society, so all my, as we all grew up, my fellow carnivorous telescope collective friends, I mean, everybody knew that Hebron Academy had this Elvin Clark. The typo was corrected in the second edition of the book. But nobody else, besides myself, around here or anywhere, bothered to visit the school. So something like 30 years later, or whatever, relatively recently, when I went back to re-inquire at the school to see if I could swap them a mead for it or something, the aging teacher there remembered me. I was the only person who had ever shown any interest in it. So he accepted my proposal for an all-too-modern telescope. So and he's very happy with his need, and I'm happy with my 6 1/4 inch Elvin Clark tube assembly. So I revealed too much of the confessions of an antique telescope collector. But yeah, Elvin Clarks can be very expensive, but there's still a lot of them, like rolling around out there on the floors of physics labs where people don't care about them, so we rationalize our compulsion by thinking that the stewardship we offer to these instruments is for their benefit as we manipulate these poor institutions. But anyways, okay, so somebody asked, I get going on a tangent, but you gotta forgive me. So all I want to do now, John. I know. So here's the thing, Astrometrica. I'm going to click on it. Click. So I made sure, got my laptop talking to the local wireless. It's wondrous. But right now, Astrometrica is thinking, and it is looking at the data file of like 150,000 orbital elements that you download from the Minor Planet Center of the International Astronomical Union. And yeah, I'm just going to replace the previous log file. So I'm giving you a very quick demonstration of how easy it is, and to me, wondrous, to do an astrometric measurement of a CCD picture. So let's open some. File, load images. And I am going to, somehow, without grounding too much, holding a control key, I'm going to open 1, 2, 3, 4, 5 images because I just happen to have them there. And these are pictures, I'll confess, of a comet. And the only processing that's been done to these pictures is the very most basic dark subtraction. They're hardly more than raw exposures. Okay, so you've got to click OK for each one. Because nowadays, with these modern cameras, the exposure time is automatically recorded in a data header that's part of the image file. All kinds of information about the telescope, the image scale, all this kind of stuff is automatically recorded with each picture. So there they are. Well, so what? And they don't look like Marios. They look pretty crude, because they are. But I tell you what I can do with this piece of shareware. I can press blink. That's blink. Let's press blink.
Is that like a bling with a K?
Maybe.
Okay.
So it's thinking on this. The files are big and my computer must be tired. Oh, there. So it's cycling through them in fairly quick succession, and this, of course, is a utility to find the dumb little bitty comet. So I'll give you all just a few seconds. There's a lot of noise, because what was the situation with these exposures? I never observed this comet ever before in my life. It was discovered by Jim Gunn. Famous Jim Gunn was the project scientist of Sloan Digital Sky Survey. He's at Princeton now. He had been at Caltech. He was one of the early pioneers of CCD technology in astronomy. He created a camera they called the Forest Shooter that ran on the Palomar 200-inch. And this is so Jim Gunn is he's one of the most famous astronomers alive today among professionals in terms of how much people are respected for a lot of stuff. Really, anyway, discovered a comet. So anybody find it? How about there? It's a little. It's not real strong, but you can see the motion. Now, the difficulty on this was the comet was already very, very low in the evening sky. And I just got the camera running and I was trying to get as much as I could. This comet was so low, even right after sunset, that I was shooting at a huge zenith distance, looking through a lot of air, and I was getting it in evening twilight and stuff. So that's why the images are so ratty. But okay, so we figured out where the comet is. But it's easier to see here in the laptop where things aren't blown up quite so much. So I close the blinky thing, and all I have to do now is go to astrometry and do data reduction. Demonstration of software can be, of course, hideously boring, so I'm not going to, so I won't talk so much. So I'm just going to say, okay, I'm not even going to try and identify the object, because you see, the software knows where the telescope was pointing. It's displaying celestial coordinates there in the window. Again, it's interrogating the so-called image headers on each of the exposures, so it knows where I was looking. And I say, okay. And that was the same for all of the shots. What it is doing right now is one of the things to me that's truly amazing. Okay? It's talking wireless right now. That bar is a data download from United States Naval Observatory. And it says, oh, it's still thinking. It knew my field of view. It knew where I was pointing. So it's going out over the internet, and it downloaded reference stars, their positions, from an astrometric catalog that's got so many stars in it nowadays that if we tried to download all those star positions into my laptop, I think it would melt, okay? No fooling. So what it has done instantly is it's circled many of the stars in green. Now, in the old days, I would have to turn screws on a microscope and put crosshairs on reference stars that I had laboriously identified by hand out of a printed book of 250,000 stars that was published by the Smithsonian Astrophysical Observatory, the most boring book to look through in the world because it's nothing but numbers. All that's been done automatically. And before, I would feel really macho and really like a good astronomer if I used like 12 reference stars rather than maybe only 6. It is so much more work to get 12, but you get a little bit more accurate reduction. You get a better reference grid with 12. But what this sucker just did is in the first frame, it identified in the frame, according to what it says there, 280 stars. And of those, 133 it has accepted as reference stars, all automatically over the internet, like a miracle, okay, from heaven. And furthermore, let me just say this. Well, it's done it not just for the image on top, but all 5 images, like instantly. How could I not be excited about that? Well, I know it's weird. But the other thing it says that I think is interesting, over here it's saying D-array and D-declination. This is like the error. So the typical error between these reference stars and the celestial coordinate grid is telling us those numbers is on the order of 1/10 of an arcsecond. Wow. That's how good the grid is relative to typical reference stars. If you do the arithmetic, 1/10 of an arcsecond, if I did the arithmetic right a few months ago and I'm remembering it right, that corresponds to the angular diameter of a dime at about 20 miles away. So that's the kind of angular measurement which is kind of coming out of this. It's pretty cool. So anyway, okay, so you go back to, make this go away. I guess I can do that. Come on, there. So you know the comet is here, and so you just click on it. Well, I wasn't really on it. There. All I did was click on it with Mr. Mouse. And what it did is it automatically computed a centroid of the comet in a magnified view, and then it's giving you some graphical indication of the signal to noise there. And it's calculated quite rigorously the celestial coordinates of the moving object of interest that you targeted based upon the reference frame that was previously established. The reference frame is good as something like 1/10 of an arcsecond. And then you say, oh, you don't know what it is yet. You click on the thing that goes ... It thinks about it. It's got all those orbital elements. And it's telling you now, because if you don't know what you're doing, you might not know what the moving thing was. But it's telling you that as far as it's concerned, the most likely thing you just clicked on, based upon previously established orbital information, was that it is object 65 periodic gun. Well, I knew that's what I was trying to shoot. But, so you go accept, you go okay, and that measurement has been written into the email, which if I hadn't done it already some months ago and contributed these data, it would be getting ready to just send. And then you feel righteous because you contributed to science from your backyard observatory, and that's kind of fun. You know, it's $35. Yes?
John, mention that AVSO reduction is now that easy as well. Everyone should do that.
Yes, I mean, of course, Astrometrica is only one example of many fantastic software utilities like ones available from AVSO for studying variable stars. At the workshop we had down in Hartless House on Friday, the minor planets and meteors, well, a gentleman came from Colorado and shown how he's doing meteor video photography and reduction of the meteor events he's recording. It's $300 to clone his video equipment for recording meteors. And then you can use an old computer, and again, it's shareware. So there are so many opportunities. Now I've spoken enough, but I just want to say, in my youth coming to Stellafane, these Friday night talks where people share in some of their special favorite things, to me, these things were always a highlight of the meeting, and I haven't had a chance to share them in a long time. I'm very grateful to be here now. So thank you.